All right. This um yeah, this one took me a bit to like actually wrap my head around. Um and I think the only way to have it click is to just do several problems. Uh and then the actual intuition becomes very obvious. So, we're taking a context-free grammar, G for the grammar, and these are our rules. So the grammar must be in Chomsky normal form, which I think was like chapter 3 or 4, somewhere in there. So every rule is either A is BC, so it's two variables, or A to a terminal, which in this case, think of terminals as a character, or technically a set of characters, some sort of substring that uh, this grammar can produce. In our case, they're all just single characters, A or B. And uh, S S is start. So that's your start variable, your starting point. You can't, like, S can create an empty string, but uh, so S is the only thing that's allowed to create an empty string. So if you're looking at any of this grammar and you see like R has the empty string here, then that means anytime that R came up, then it would just delete the string. So that's not really a rule that's useful. So in Chomsky normal form, that's not allowed. And then S can be a terminal, but then S is a single character language. So in this case, if you're like, can this produce BABA, and you have a rule that says start translates to A, then obviously no, because the only thing it can produce is just A. So that's not normally a a part of how these are expressed in Chomsky normal form, but I suppose that's something for you to look out for if you're messing with these dynamic programming things. If you end up with a starting point that is either the empty string or just a single character or subset substring, then you know, like, if it reduces down to that, you go no further. That's the end of the road. And then, so that's why when we're looking at these, the typically you'll see them being two variables. So this is more or less saying that we're taking two chunks of something and putting it together. And that's going to be in the normal form there. So a variable can be terminal, or it's going to be two variables. Otherwise, you can't build anything with it. So G, and this is a check, like, this table structure that we're going to do doesn't work if it's not in Chomsky normal form. So those are things that you need to actually look at the grammar for ahead of time. You need to like look through it and be like, okay, are all of our expressions here, are all of our set of rules here, where S is not an empty string, S is not a terminal. S always has to be two variables, and then the variables themselves can be two other variables or a terminal. And that's what this notation is. So two variables and a terminal. And then I guess technically something that can come up is if you see a variable that translates to a variable that's not inside the grammar, then that's also a red flag, and that violates the CNF form. So the data structure, the actual algorithm is, if you're looking at this and you haven't worked through any of these, then this makes no sense. So we'll come back to this, and then we'll look at it. So we need a table that, so we have our BABA, and So back up here, we get B from T, and we get A from R. So that's basically all this table is saying is TR, TR. And so step 2 is we're going to split the points. And again, this goes back to the algorithm at the beginning and why it's all 2n minus 1 and for the length of everything and how that kind of like, you know, the math of it. But actually doing this on a test, I would not be trying to look at this in terms of the math and the proof. I would be looking at this in terms of how do I build this to prove that it works. So basically, we're just going to make a table of rules, which we already have. We're just going to take these and we're going to make that a little reference lookup. And we're going to come down and fill out a table. So when we're doing this, basically what we're looking at is we're going to start at the bottom. In this case, I think it was what? So we had BA. So if we're looking at the bottom, we got BA. We're going to figure out what can produce each piece of this. So first thing is just going to be what makes B. And that's easy. We just have T. What makes A? R. What makes B? T. What makes A? R. So the next part gets different. So we're going to be looking at the entire substring here, BA. And then we have to write in here what makes that substring BA. And then we're going to look at AB, and then we're going to look at BA. So this actually grabs a little triangle, basically. And then, so it's going to take these two blocks and then push them up. And then up here, it'll take the 3 blocks and then push them up. And this basically takes all 4 blocks and then pushes them up. So we finish this table and we're going to end up with RT. And then since AB is different, we can actually condense that back up to the rule of RT. So RT condenses back into S, S being our starting point. So that's why we see S here. So in this table, if there's only 4, it's going to be at length 3, where we're going to start looking at the Cartesian products of those. So we have RT and S. So then when we take those products, the RT and the S, then we're going to look at that, and it's going to be either the RT, which condenses to S, or S, which condenses to S. So then we put that S back in that row. That takes a little bit of practice. So don't, like, this is not an intuitive thing the first time you do it. But what you're doing is you're taking each possible set of substrings and you are condensing them back to, okay, where can we start this, and then what are the 2 parts of the substring that can then build out. So it's basically recursion, but backwards. We're starting, like, it depends on how you look at recursion, but we're breaking it into smaller problems and then seeing if each of those smaller problems can be solved. So then if we end up with any possibility here, if we end up with a non-blank box here that starts with S, because it obviously has to start with start, then we can say that this this string is in this grammar. And that's more what this actual math up here is saying, is when we have these substrings, we're going to split them, and then we're going to have each part of that substring, and then we're going to take each substring and split it and see if we can come up with a rule that will create that substring, and then we split that and see if there's a rule that comes up with that substring, and then we split that and we see if there's a rule that comes up with that substring. So the math kind of expresses this as you're going forward, like you're taking the entire string and then you're splitting it, and then you're splitting it, and then you're splitting it. But the problem with doing it forwards is you don't know where that split needs to be. Like, depending on where you pick that pivot, you may end up in a case where you're breaking those rules. So instead of trying every single pivot to see if you can come up with a set of rules that will build that string, we just do it backwards. We take every smaller part of the string and we prove, yes, we can make every single part of this string up into the starting point, which will kick off each part of the string. So that's how that works. And then my little blurb here to sum it all up. CYK is a bottom-up dynamic program for CFGs in Chomsky normal form. It collects every variable that derives the string, the entire string, computed from shorter substrings by trying every split K against every rule A map to BC for our string BABA under this grammar. The table fills with sets that grow as we widen the substring, and it shows that 1,4 being the top of the box is SRT. So it has a start, and then we have strings that can fill in. So BABA is in the language of G. So yes, and I'll do a separate one for 7.5, but it's very short.